So this talk for the first half will be basically a review talk on how Quiver gauge theories are related to Toric Calabi-Yau manifolds in general. In particular, 2D 0,2 Quiver gauge theories related to Toric Calabi-Yau manifolds. And then the last part of the talk will be on an observation that we made earlier this year on how birational transformations existing in birational geometry connect to these Toric Calabi-Yau manifolds associated to these 0,2 Quiver gauge theories. So as you introduced me at the beginning of the talk, I'm from UNIS. UNIS is one of the 4 institutes of science and technology in Korea. So if you come and visit us in Korea, please come also to Ulsan. Ulsan is a city very close to Busan, which is about 2 hours away from Beijing. So it's very close from here at Tsinghua University in general. So the talk that I give today is based on 2 works mainly, with my collaborator Dong-Woo Kim, who is in Weekend, as well as my graduate student, Ms. Sung Ko. One paper that came out at the end of last year, as well as a paper that came out earlier this year. So when first introducing my talk, let me first review what we mean by Toric Calabi-Yau manifolds in general. For those of you who may not know much about Toric geometry, if we start with a lattice polytope, let's say a convex lattice polytope in a Z2 lattice, we can lift such a lattice polytope 1 dimension up on a hyperplane at height 1. That naturally allows us to define a cone with the inclusion of the origin of the resulting Z3 lattice. That cone has a natural dual cone, which is mathematically defined as follows. And through this dual cone, which is also in a Z3 lattice, we can define something known as the semi-group algebra, which forms something we know as an affine toric variety, in this case, an affine toric threefold. And this also turns out to be Calabi-Yau due to the fact that the construction resulted in the fact that the generators of this variety were all lying on a hyperplane at height 1. And this can be done not only for polytopes that are embedded originally on a 2D lattice, but also convex lattice polygons in any dimensions. In fact, I can start with a convex lattice polytope in n-1 dimensions, and that will be then lifted into an n-dimensional lattice. Through the dual cone, I can write down an expression of the affine toric variety, which results in something we know as a Toric Calabi-Yau n-fold. So starting with any convex lattice polytope, I can associate that polytope to an Toric Calabi-Yau n-fold. And these n-folds have been studied by mathematicians, by Toric geometry, people working in Toric geometry extensively, and they have been also classified. One famous classification done by Batirev in the early 90s was a notion of reflexivity. So a convex lattice polytope which has a single internal point, the origin of the lattice, is known to be a reflexive polytope. So it has a dual polytope and a dual lattice, which is also a reflexive polytope. So here in this case, I'm showing you an example of a Z2 lattice. This is the toric diagram of the F0 hexabox surface. And the dual polytope is an orbifold of the conifold. So you can classify these reflexive polytopes, and they exist not only in 2 dimensions, but in 3 dimensions and higher dimensional lattices. And we have been, so here you can see the lattice polytopes in 2 dimensions. There are 16 of them that are reflexive. In higher dimensions, you can also have a classification of the form. These are reflexive regular polytopes with 1 internal point in a 3-dimensional lattice. So in fact, the classification for these such reflexive polytopes has been done by Koiter and Strake. In fact, they have been classified up to 4-dimensional lattices. And for the reflexive cases, in 2-dimensional lattices, there are 16 of them. For 3-dimensional lattices, there are more than 4,000. And for 4-dimensional lattices, there are nearly 500 million of them. A subfamily of these reflexive polytopes are regular polytopes. So these are polytopes that have only corner points on their boundary. So for instance, these ones are the so-called 18 regular polytopes in dimension 3. And these reflexive polytopes are known to result in affine toric varieties that are known to be Fano. So if I have a lattice in n-1 dimensions, they give me a Fano n-1 fold, and they're all related to toric. They are forming a subfamily of toric Calabi-Yau and folds in general. So this is a very interesting family of Calabi-Yaus, toric Calabi-Yaus. Obviously, there are infinitely many of them for reflexive or Fano varieties, which are toric. There are finitely many. So from a point of view, not just from toric geometry, but also from differential geometry, you can think of these toric Calabi-Yau n-folds to be real cones over a Sasaki-Einstein manifold. So for a Calabi-Yau n-fold, this is a 2n plus 1 dimensional, real dimensional Sasaki-Einstein manifold. And for some of them, the metric is known explicitly. Because this is a real cone, you have a conical singularity, which can be probed in string theory by an appropriate brane. So if I have a Calabi-Yau n cone, an n-dimensional cone, which occupies 2n real dimensions, then in string theory, I have 10 minus 2n dimensional remaining, which can be occupied by d9 minus 2n brane. So we call these probe brane that we can put on the conical singularity of such Calabi-Yau n-folds. So now we have geometry meeting string theory construction, one of the simplest here, where I'm probing with the brane transverse geometry, in this case, occupied by a toric Calabi-Yau n-fold. So we can, because we are in 10-dimensional string theory, this gives me the following non-trivial configurations. If I have a toric Calabi-Yau threefold, that can be probed by a D3 brane. The dynamics of this D3 brane is described by a 4-dimensional n equals to 1 supersymmetric gauge theory, which I can write down. The corresponding Lagrangian can be written from the geometry that I have here. I can also have a toric Calabi-Yau fourfold. Then the transverse directions can be occupied by a D1 brane. The dynamics of that D1 brane probing this Calabi-Yau fourfold is described by 2D0,2 supersymmetric gauge theory that I will tell you a little bit more about later in this lecture. Last but not least, in the last few years, we conjectured that we can also have a toric Calabi-Yau fivefold that can be probed by a D-1 brane. And that D-1 brane has a word volume theory, which we expect to be a zero-dimensional matrix model, for which we also have some examples where we write down the corresponding Lagrangian of the zero-dimensional theory. This will be not the topic of my talk here, but let me tell you a little bit at the beginning of my talk about how 4D n equals to 1 theories come about when I have a toric Calabi-Yau threefold, and from that, how the 2D0,2 Quiver gauge theories come about from D1 branes probing a toric Calabi-Yau fourfold. So for this 4D n equals to 1 theory, I can write down the corresponding 4D Lagrangian. The unique parts of the Lagrangian come from the set of chiral fields and the superpotential that is formed by these chiral fields. And using this Lagrangian and the information that uniquely defines this Lagrangian, I can write down the so-called moduli space, vacuum moduli space of this Lagrangian. In the case when I have a single D3 brane, these chiral fields are transforming under representations of or gauge groups, which are U1 gauge groups. So from there, I can write down algebraically a coordinate ring parameterized by the chiral fields of my Lagrangian, subject to the vanishing F terms of the superpotential that I have in my Lagrangian. And that coordinate ring is then graded by U1 gauge charges that then I take out by GIT quotient, resulting in a variety that is associated to or is equal to the Toric Calabi-Yau threefold that we start with. So given the Lagrangian, we identify what the corresponding Toric Calabi-Yau threefold is. And for instance, here is an example of the set of chiral fields that I could have for a corresponding 40N1 field can be described by a Quiver diagram. The nodes here represent gauge groups, in this case U1 gauge groups. I have 4 of them. The arrows correspond to bifundamental chiral fields that transform in bifundamental representations of these U1 gauge groups. So these are arrows. The direction tells me which representation I'm taking in. Because I have U1 gauge groups, the charges under these gauge groups are all plus and minus 1. So you can think of this as the adjacency matrix of this graph that represents the Quiver diagram. And I can have also closed loops. My construction. So in this, these closed loops correspond to gauge invariant operators in my supersymmetric gauge theory. So these are as identified by either positive terms or negative terms in my superpotential. So you can see there's a lot of combinatorics happening here. The idea is that from this information, the data of the chiral fields, how they transform under the gauge groups, and the superpotential data, I can compute what the corresponding Calabi-Yau threefold is that is pulled by the D3 brane. One interesting thing is that this D3 brane probing this Calabi-Yau threefold, this configuration is T-dual to a configuration of D5 branes suspended between an NS5 brane. Here the Calabi-Yau threefold under T-duality becomes basically an NS5 brane wrapping a holomorphic curve, which I call here sigma. This holomorphic curve is parameterized by 2 complex coordinates x and y, which are in C star. I can write down these 2 coordinates in terms of the 4 space-time directions, 4, 5, 6, and 7, in which the D5 and NS5 branes are meeting. One neat thing is that this curve is also known as the so-called mirror curve of the Calabi-Yau threefold. So in fact, there is an analogous mirror description of this configuration that I will not go into in my talk today, but at least note that this curve is also known as the mirror curve of the Calabi-Yau. So one thing that I can do is I can actually visualize how these D5 and NS5 branes meet along this holomorphic curve. I can actually project this curve onto a 2 torus by taking only the angular coordinates of x and y. These angular coordinates are parameterized at 2 torus, where now the curve itself tells me the location of the NS5 brane projected onto this 2 torus. And the plane of this 2 torus itself is the D5 brane that's suspended between this NS5 brane wrapping this surface, this curve sigma here. In fact, this construction is also this brane configuration on this 2 torus is also identified with a so-called bipartite graph on the torus known as a brain tiling, or in the math literature as a dimer model. This talking about this dimer model itself is a talk on its own, so I'm just hinting at it. But the important thing is that the curve that you obtain from the Toric Calabi-Yau threefold essentially tells me the brain configuration of D5 and NS5 brains that realizes the corresponding 40n equals to 1 theory given by the Quiver diagram and the interaction terms encoded in it. So how do I define this mirror curve? In fact, it's defined by the zero locus of the polynomial in x and y. This polynomial is also known as the Newton polynomial coming from the toric diagram of the Toric Calabi-Yau threefold. It's basically a generating function, a finite generating function of the vertices of the toric diagram. The vertices have coordinates in Z2, which are integer, and I'm basically counting these coordinates by the variables x and y, where the exponents of x and y are given me the coordinates of these vertices. So for this example of the Hertzsprung F0, I have 5 vertices, so I end up with 5 terms in my polynomial. And this, when this polynomial is set to 0, the set of solutions then define what I call as the Calabi-Yau mirror curve, the sigma. In fact, I also have a non-trivial complex coefficients in this polynomial, which I here call C1 and C2 for this F0 example. These are the so-called complex structure moduli of the associated with the Calabi-Yau field. I can do the same exercise for higher dimensional Toric Calabi-Yau curves. In this case, Toric Calabi-Yau fourfold. This is the toric diagram of Q1 over Z2. It contains 7 vertices, and each of these 7 vertices, it gives me 7 terms in a Newton polynomial parameterized by 3 complex coordinates x, y, and z. When I set these polynomial to equal to 0, I get something parameterized in 3 real dimensions. We call this as a mirror curve, a mirror surface, sigma, identified with the Toric Calabi-Yau fourfold given by this toric diagram. So you can now see that in theory, I can define for any higher Toric Calabi-Yau mirror hypersurface given by sigma. Using that hypersurface, can I construct an analogous brain configuration that I had when I had Toric Calabi-Yau threefolds that generate via a brain engineering construction a corresponding Quiver gauge theory. And that was the idea here. When I go to Toric Calabi-Yau fourfolds, I can probe the singularity by a D1 brain. The corresponding gauge theory is expected to be a D0,2 gauge theory. Using the mirror surface of the Toric Calabi-Yau fourfold, can we construct the associated D0,2 gauge theory information? And in fact, the answer is yes. If I look at the configuration of D1 brains, probing my Toric Calabi-Yau fourfold, I can T2-alize this along 3 directions, giving me there should be a D4 brain. D4 brain suspended between an NS5 brain, where the NS5 brain now wraps a homomorphic surface, my mirror surface, associated to my Toric Calabi-Yau fourfold. The mirror surface defined by the zero locus of the corresponding Newton polynomial of the Toric Calabi-Yau fourfold itself. So I can actually visualize this if I project the 3 complex coordinates x, y, and z along the angular directions, theta x, theta y, theta z, which parameterize now as 3 torus. I can now actually visualize the shape of the mirror surface wrapping the 3 torus, and that picture then tells me exactly the location of the NS5 brain wrapping the 3 torus. and the D4 brane suspended between that N5 brane. So, yeah, so at the moment, I'm just looking at the single D1 brane probing this Toric Calabi-Yau fold. I can obviously have n D1 branes or fractional branes. I'm not considering that at the moment. I'm just looking at the simple example. Obviously, the generalization is so possible. The computation obviously will become more difficult. So here I'm basically drawing this projection of the mirror surface as a cartoon on the free torus. So there's a blue, these blue lines basically tell me the shape of the curve of the surface wrapping these two torus. The interior of this polytope basically is telling me the location of the D4 brane that is suspended along this NS5 brane wrapping this polytope representing the location of the holomorphic surface on D3. And in fact, you can then, under a process that I'm not going to go too much into detail, is I can associate orientations along the surface wrapping the three torus. Under these orientations, I can have areas where along the surface that are oriented in either a clockwise or an anti-clockwise manner. This orientation tells me how the D4 brane realizing a U1 gauge group in this 2D 0,2 theory charges a corresponding chiral multiplet either in the fundamental or anti-fundamental representation. I can also have regions on the surface that are unoriented. In fact, these regions are now identified not with chiral multiplets, but so-called Fermi multiplets, which come to existence when you go down from 4D gauge theories to 2D gauge theories. So this cartoon that we draw of this brane configuration is what we call as a brane ring model. We identify phases of polytopes to either chiral or Fermi multiplets of my 2D 0,2 theory, and the interior regions of these polytopes are identified with gauge groups, U1 or UN gauge groups of my 2D 0,2. So, so this is an example of C4. So if I just look at C4 and write down the surface and project it onto the features, it can be represented by what is known as a truncated octahedra. This is a polytope that tessellates the features without leaving any gaps, and it's made out of 8 hexagons and 6 squares. It's one of the polytopes that tessellates the features. In higher dimensions, this story becomes more difficult. So, then exactly. So yes. So if you go to Calabi-Yau 5 folds and the 4 torus, that there will be an analogous convex polytope in 4 dimensions that tessellates the 4 torus uniquely. I don't remember the name exactly, but I do. There is an analog of that in C5. But that's not the topic of my presentation today. But thank you for the question. But yeah, here you can see that this truncated octahedron corresponding to C4, the simplest Calabi-Yau 4-fold, is tessellating this features uniquely. And you can see that areas that correspond to Fermi multiplets, which we here represent as a square, are connected to areas that are associated to chiral multiplets. And in fact, if I look at opposite edges of these Fermi squares, they are associated to monomial products of chiral multiplets that identify either a so-called E term or a J term of the corresponding 2D 0,2 Lagrangian. So this is neat. One thing that is important here is that these Fermi multiplets as part of a Quiver diagram are unoriented because Fermi multiplet can be swapped with its conjugate Fermi, and it's still under this conjugation, the Lagrangian of the 2D 0,2 series remains invariant. So it's represented by the same object in this configuration that we have here. So here you can see the whole story. For every Fermi multiplet, I have two pairs of monomial products of chiral multiplets that form with its associated Fermi multiplet four distinct closed loops in the associated Quiver diagram. They can be combined along the Fermi multiplet and its conjugate to form two binomial relations which are associated to the J and E terms of the corresponding 2D 0,2 field. So the role here of the Fermi is not to actually parameterize as coordinates the associated toric variety, but rather to label where the corresponding binomial relation should be in terms of the chiral multiplets of my 2D 0,2 field. So again, if I have now my chiral multiplets and my Fermi multiplets associated to a pair of J and E terms, the corresponding 2D 0,2 Lagrangian is uniquely identified. With that information and how they transform, how the chiral multiplets transform under the gauge groups, I can write down the corresponding coordinate ring of the variety that is associated to the Toric Calabi-Yau fourfold. Physically, that means the vacuum moduli space of the 2D 0,2 theory. So here, important, again, the J and E terms are all binomial. They form, therefore, a binomial ideal that it gives, by definition, a corresponding toric variety. In this case, an affine toric variety of the Calabi-Yau fourfold. So here is a comparison, right? I have 4D n equals to 1 series corresponding to Toric Calabi-Yau threefolds. They are represented by plane configurations called plane tilings. They have vector chiral multiplets and a superpotential giving me binomial F terms that define a Toric Calabi-Yau threefold. I have also a 2D 0,2 series associated to Toric Calabi-Yau fourfolds, whose plane configurations we call as plane big models. The elements here are vector chiral and Fermi multiplets, where the Fermi multiplets are associated to a pair of J and E terms that are binomial that define an associated affine toric Calabi-Yau fourfold. Oh, yes. No, they can have obviously higher order. Yes, I'm only showing you examples so that this picture is. But yes, they can have arbitrary high order that will have an effect on the associated R charges on the J and E terms, which will be an issue later on. But yes, that's a very good question. Thank you. But important thing is by construction, everything is binomial, therefore we are associated to Toric Calabi-Yau fourfolds. So here is an example. This is the Toric Calabi-Yau fourfold associated to Q1 over Z2. This is the toric diagram with its Newton polynomial. The J and E terms, as you can see, are now quartic and quadratic to cubic. And I can draw the corresponding Quiver diagram with Fermi and chiral multiplets indicated in different colors. This is the actual, technically, this is what we call a periodic quiver. It's the dual graph of the brane configuration mapping T3. And if I pick here an example, this Fermi multiplet between gauge group 7 and 2 is associated to an E term, which form two closed paths associated to this Fermi multiplet between 7 and 2. I have also a J term They correspond to two closed paths that also link gauge groups 7 and 2 associated to the same Fermi multiples lambda 7, 2, 1. So you can see this J&E terms, set of J&E terms identify a set of closed paths in a periodic quiver wrapping free torus. And from a mathematical point of view, you can also write down the associated quiver algebra. And the idea here is that that quiver algebra will also be a Calabi-Yau algebra. In fact, that Calabi-Yau algebra on this quiver is expected to be associated to the same Toric Calabi-Yau 4-4 that it starts with. I can simplify this periodic quiver on T3 into a single quiver without the periodicity, and that will be then my data set, the Toric Calabi-Yau 4-4, the quiver diagram of the 2D 0, 2 theory, and the J&E terms. Here's another example. We call this the gets above F0 lifted in plus and minus directions. The Toric diagram is of this form, and the quiver diagram is this, and the J&E terms are, you can now see the J terms are all cubic and the E terms are all quadratic. So this, so this is not the complex structure moduli. This is I identify as I can put it as one. This is or any other complex number. It's actually the internal point of the Toric diagram that I have. I can put the one or whatever. I can. There's a theorem that for Calabi-Yau 4-4, or in general for Toric Calabi-Yau n-folds, I will have a finite number of independent complex structure moduli. That is, and that number is dependent on how many vertices I have in my Toric diagram. Yes, so it's a particular point in the modular space, and that choice will be explained later. So, but I'm just showing you that what I choose for C here for my remainder of my story will be not important, but here the 2 will be important. Any other questions? Mm-hmm. Mm-hmm. Yeah, so this will I can get rid of 4 variables in total because right. And I would remain with 3 distinct complex structure moduli that are independent. But here I'm not really into complex structure moduli. I'm just taking 2 of them to be U and C, and the remainder will be 1. I'm not doing the mirror symmetry story here. I'm doing something different, which I will tell you a little bit later. But yes, I can do use this polynomial for the mirror Calabi-Yau mirror construction of these corresponding T3. The reason why I'm using this particular parameterization is due to quite an impressive tour de force by 4 mathematicians in 2012. I quote Starkin and Kirich. And they have introduced in 2012 a family of so-called birational transformations. These are birational maps that act on the Newton polynomial of a family of Toric Calabi-Yau 4-folds, in fact, Fano 3-folds. So these are reflexive polytopes in 3 dimensions. We know that there are 4,319 of them. And for each of these 4,319 of them, they identified a map, which we call here as phi A, that transforms the Newton polynomial P of x, y, and z into a new Newton polynomial, Px, y, A of x and y times c, where A of x and y is a subnormal polynomial that satisfies this condition here. So I need to first write my Newton polynomial of my toric diagram in this particular expansion in terms of order parameter z. And then the coefficients will be Laurent polynomials in x and y, labeled by an index n that has to satisfy this polynomial division condition in terms of a new Laurent polynomial a of x and y that then I use to reparameterize my Newton polynomial into a new polynomial p of x, y, and a of z. Why is this interesting? I can use this algorithm of defining such birational transformations for a particular toric diagram delta. It will have a Newton polynomial, which can be written in a particular modular chamber, can be written in this particular form. In this particular form, it will then have an associated birational transformation, which then will give me a new Newton polynomial, which can be then interpreted in terms of a new convex lattice polytope on C3. So this an example here is as follows. The two toric diagrams that I showed you earlier are related by such birational transformations when the corresponding Newton polynomials are mapped by phi A and its inverse. I will show it later. But here the main point here is that these for mathematicians went through all 4,319 reflexive polytopes in dimension 3 and shown that out of these 4,319, 3,025 of them form equivalence classes. In fact, they subdivide into subsets that are all related by a family of birational transformations. So within such a what they call a bucket, you can have a set of birational transformations that map these polytopes within a bucket into each other, but you cannot leave the bucket into another bucket, and they are actually distinct from each other. So in fact, out of these 3,025, they found 165 distinct buckets of toric diagrams that are mapped to each other and do not communicate with each other. Exactly, yes. So this is all part of the minimal model program. It's a version of birational mapping between toric varieties. And in fact, in this paper, they identify that the corresponding toric varieties within the same bucket are so-called deformation equivalent, meaning that they form a set of vibrations over some parameter space, and you can transform one toric variety into another toric variety in a continuous manner. So they are related, and toric varieties that are in different buckets cannot be deformed into each other. So this is the idea that we are having here in terms of birational geometry. And now we have these sets, subsets of reflexive polytopes corresponding to Toric Calabi-Yau fourfolds that are mapped by these birational transformations that we have here. Yes, so I will tell you what the properties are of this birational mapping that we are having. Before telling you these properties, let me show you this example that Armin asked earlier. I start with this polytope of F0 projected to plus and minus. This toric diagram has this Newton polynomial that allows me to define this birational map where x, y, and z is mapped to x, y, and a of z, where a is 1 plus 1 over y. That results in this Newton polynomial, which has some oddities in terms of toric diagrams, but I can transform it by an appropriate GL3Z transformation to a nice form, which is this Newton polynomial that gives me the toric diagram of Q111 over Z2. This is what, so this additional step of GL3Z is necessary to make this form a bit neater. So with the combination of GL3Z mapping, this transformation is also referred to as an algebraic mutation by these four mathematicians. So here, as you asked, under these birational transformations, you have multiple mathematical quantities that are preserved. First of all, if I start with a reflexive polytope, under this birational map, I will get another reflexive polytope. So I will never leave the set of 4,319 reflective polytopes. And within the same equivalency class under these birational transformations, the so-called period integral of the associated toric variety is also preserved. And we know this period integral is related to corresponding, in the case of Toric Calabi-Yau free folds, this period integral is related to partition functions of associated gauge theories, including partition functions counting Robert-Fitton invariance. So this is something interesting to look at from a mathematical point of view. Then there's something called an Erhard polynomial that you can associate to a lattice polygon. The Erhard polynomial is basically a generating function for any n-fold enlargements of, it's basically the generating function counting the number of vertices in my polytope when I'm enlarging this polytope by a lattice grading of M. And I can also add what I earlier said before, is that the associated toric varieties within an equivalency class are so-called deformation equivalents. So there's a continuous deformation that you can define that relates toric varieties associated by this birational transformation. So these are the mathematical results that were presented in this paper. We now have the two questions that we want to answer. What are these implications associated to the corresponding quiver gauge theories that I talked earlier about, the 2D0,2 gauge theories? And can I also, as part of the second question, talk about Toric Calabi-Yau folds that are not necessarily associated to reflexive polytopes, and can those reflexive, non-reflexive polytopes have also similar properties under birational transformations? So one thing that you can look at are these two examples that I showed you that are related by birational transformation with these two toric diagrams have the following 2D0,2 quiver diagrams. And when you look at them, which I showed you earlier with the corresponding J&E terms, they are related up to Fermi-chiral pairs in the quiver diagram. In fact, if I delete all the Fermi-chiral pairs, I get the new quiver diagram associated to the new Toric Calabi-Yau folds that I obtain under this birational transformation. And removing these Fermi-chiral pairs in the 2D0,2 theory is basically equivalent to mass deformation in 2D0,2 theory. I can add mass terms associated to the chiral field in each of these Fermi-chiral fields into the J&E terms, and under these mass terms, which then I can integrate out, I end up with a new set of J&E terms that correspond to the new 2D0,2 theory under this birational mapping. So the expectation now from this result is that every mass deformation of this form in 2D0,2 theory is associated to a corresponding birational transformation of the corresponding toric varieties. But the other way is not necessarily true. There might be birational transformation in the classification by Tom codes that may not necessarily relate to mass deformation. And that is what we are also trying to do in the future. But for the moment, every master formation in 2D 0,2 Quiver gauge theory associated to a Toric Calabi-Yau fourfold can be interpreted as a birational transformation of it. Because I'm adding mass terms in either the J or E terms of the 2D 0,2 theory. These are singlets in the it's in quadratic in the coupling when I look at the Fermi E coupling. So in the superpotential of the 2D 0,2 theory, they appear as Fermi E plus conjugate Fermi J. Right? So in that sense, they are mass terms, analogs of mass terms. Right. Which then I integrate out to get the new J. Uh-huh. Mhm. Uh-huh. Oh, that's a very good question. So this now relates to whether I have branching points in the birational transformations that I have within a bucket. So I will have multiple Toric Calabi-Yau fourfolds that are related not just in a linear fashion, but also in they form very intricate trees with loops. So for each of these birational maps within this graph, we might have a deformation. Some of them are mass deformations, not all of them might be mass deformations. They will be related to some other deformations, which we hope to classify in the future. But yes, that's a very good point. How do I go the other way around? Again, I have degrees of freedom of how to add Fermi chiral fields into the quiver diagram without breaking without with the condition of anomaly cancellation included, that obviously I have multiple choices, and these multiple choices might relate to branching points in the birational transformation class that you have within one bucket. So yes, it's a very rich thing. I mean, Tom Coates has in his paper with his collaborators classified all of these buckets, and each of these buckets will relate to relationships with at least one 2D 0,2 theory for each body twig. So one point that we learned was that mass deformation for 2D 0,2 theory corresponds to birational transform corresponding toric varieties. The other is the following. You can compute the Hilbert series of the corresponding Toric Calabi-Yau form. The Hilbert series is a generating function of graded graded vector spaces that you have in the coordinate ring of the variety. But if I use the grading of the Hilbert series corresponding to the full global symmetry, the Hilbert series are not the same because obviously the Toric Calabi-Yau fourfolds are not the same. However, if I remove the so-called favor symmetry, global favor symmetry, and just leave the U1R symmetry of the 2D 0,2 theory, then something magical happens. If I have only fugacities of the U1R symmetry, then the Hilbert series ends up identical. So, so these are two where T1 and T2 correspond to irrational R charges that we cannot so these correspond to two different values of R charges of gauge invariant operators, so which I did not refine into a single one. So these are just parameterizations of the R charges that we have. But the key here is that this is basically identical, or at least related to what is known as the Erhard polynomial. It's basically counting along the weak direction how many generators I have for a given degree in my coordinate ring. So that's a good point. So if I turn on the remaining global symmetries, is there a map between global symmetry charges from one side to another that has not been identified so far? Let's call it that way. But what the mathematicians have told us is that the Erhard polynomial is the same, and the Erhard polynomial is basically the generating function of generators of my moduli space parameterized along the read direction. That's what we have here. So that's sure we can say whether there is a more general thing for the full global symmetry grading is the open question. But yes, so the U1R symmetry with finite Hilbert series remains the same under birational equivalence. Last but not least, because of that identification of Hilbert series refined only under U1 symmetry, U1R symmetry, there's a resulting correspondence that in fact I have 4 polytopes, the original toric diagram, the birationally equivalent toric diagram, delta V, but then I have, because they are reflexive polytopes, the polar duo reflexive polytope delta circle, which is also known as the lattice of generators of the corresponding toric variety. I mean, either from a mathematical point or from the gauge theory point, that's what we call as the lattice of generators. It's a polar dual polytope. And the polar dual polytope, every point is a generator moduli space. And the number of points in the dual polytope is preserved under this birational transformation, meaning that the number of generators that I have before and after of the birational transformation is preserved. So you can now see as part of your an answer to your question, there should be if there is a transformation under the global symmetry, there should be a geometric transformation from one lattice generator of lattice to another generator lattice, meaning there should be a birational transformation on the dual polytope, polar dual polytope of the toric diagrams related by this birational transformation. Yeah. So these are so this is one of the smooth ones, right? But then under this birational transformation is mapped to a non-smooth one, right? So yeah, the 18 do not mingle with themselves only. They mingle. So that's a different question. It's not part of my talk, but yes, again, that is also studied. Lower dimensional birational transformations are also studied, and the 16 map into distinct subsets, which are related by mass deformation of the corresponding 4D equals to 1 theories. That was work by Stefano Cremonesi and a student a couple of years ago, where they not only looked at mass deformation, but also marginal deformations that also map to birational transformations of Toric Calabi-Yau. Anyway, that's right. So, basically, that's a different story, and in fact, that's a very interesting story that I am probably not going to. This Stefano also and Sebastian Franco are all involved in the lower dimensional Toric Calabi-Yau 3 case. Here in the Toric Calabi-Yau 4 case, that originally was the topic of birational transformations by Coates and al. Is what we are here trying to do in easier context. So yes, so last point was that in fact we have in our work looked also cases that are non-reflexive. So these are Toric Calabi-Yau folds with toric diagrams that have 2 internal points. They are not Fano, toric Fano, but still I can try to identify the corresponding 2D 2 views. It becomes rapidly very complex. You can see how many different gauge groups and fields I have, but I can still identify the Fermi chiral pairs that relate the two, and I can associate to each of these family child pairs an additional mass term that I can add to the E terms. By integrating them out, I go from one to the 0,2 theory to another 0,2 theory. So again, yes, I can do this. There are birational transformations that I can define that go from non-reflexive to non-reflexive, and the corresponding 2D 0,2 theories are also identified by mass deformation. And again, I can also compute the Hilbert series. They are identical. The number of generators are also identical under these transformations. So in fact, yes, so that relates to Armin's question. In fact, all these 2D 0,2 theories have can be constructed from a 4D origin, right? I mean, the simplest thing is I can dimensionally reduce a 4D n=1 theory to a 2D 2,2 theory. Then I can break the supersymmetry to 0,2 by an additional orbifolding. We call that orbifold reduction. You can also do other things. So also what Sebastian and Hassan have been doing is 3D printing, where you can glue layers of Calabi-Yau free folds together, and their associated 4D n=1 theories to cook up various other 2D 0,2 theories corresponding to more complex Calabi-Yau four folds. In fact, we also have identified infinite families of 2D 0,2 theories corresponding to YPQ manifolds. These are now codes over Sasaki-Einstein 7 manifolds for which the metrics are explicitly known. So for all of these families, we expect birational equivalence to exist also in the context of 2D 0,2 theories. And in fact, in 2022, we have classified the corresponding 2D 0,2 theories associated to the 18 smooth reflexive polytopes in dimension 3. And for these, we expect all of them to exhibit birational equivalence to other Toric Calabi-Yau four folds. Also, in many years ago with Kommun, we have been also studying all these theories in the context of Calabi-Yau mirror symmetry. So again, under Calabi-Yau, from the mirror point of view, when you start to change the coefficients of the Newton polynomial defining the mirror curve, the complex structure moduli, you end up generating transitions. And these transitions of branes wrapping these mirror curves are identified in the case of Toric Calabi-Yau free folds as Seibert duality between 4D n=1 theory. In the case of 2D 0,2 theory, they are identified with virality by Gadek, Gukov, and Putrov. And in the case of Calabi-Yau 5 folds, they are identified with so-called quadrality with between the theories. So now the question is, how is this related to birational equivalence? So I have on one side gauge theory duality, on the other side I have birational equivalence. Do they mix with each other? That's one question that we would like to answer. And the other answer is, are there other quantities? So for Professor Yau, we have been studying bounds on various geometric properties like the volume of the Sasaki-Einstein manifold. How are these geometric invariants also related under birational equivalence? And that's one thing we are studying, not just the volume, also so-called Futaki invariants might be affected by such birational transformations. How are these then related to quantities of the associated gauge trees? With that, that's the end of my talk. Thank you for your attention.
Okay, thanks for the nice talk. Are there any questions?
Hi. So my question is really about the. So you are studying the brain probe theories.
Yeah.
But my question is more about the closed string physics. If you remove the branes, what do we know about the physics of type 2B theory on these cones? or resolutions of these cones?
So,
And how does that enter
so-
into the brain theory?
so I was looking at the ones probing Calabi-Yau fourfolds. So the associated brain configurations are type 2A configurations, and in that context, so I believe you may.
No, I mean, like, so you're doing D1 brains in type 2B theory.
Yeah, sorry. So,
Sorry.
but the D4 and its 5 configurations are type 2A. But anyway, and so in that
Okay.
context, yeah, so type 2A or type 2B, in whatever context, again, how this is related in the context of ADS-CFT correspondence, that's again a big question mark. In fact, it's one of the things that we are also trying to understand. For instance,
Does
can
it
we
look-
compute the
These, if I just look at these examples,
you mean
these have
okay.
D3 brain instanton
Mhm.
corrections.
So these are D1 brains on Calabi-Yau 4.
Yeah, I just mean if I have type 2B theory on this Calabi-Yau fourfold, for example, it's YPQ CP2,
Why?
you can have D3 brain instantons wrapping the CP2 and things like that.
The space, yeah. So for the space of couplings, it's still something that we have to look into.
Because in general,
so at the moment, all the couplings that we have, we turn them to what equal.
and also,
one.
so some of the couplings are actually dynamical fields and some of them are not.
Right.
And that depends on the details of the asymptotically conical Calabi-Yau metric that you have.
So one thing we can do is we could compute, what we have done is we computed the elliptic genus of the corresponding 2D 0,2 theory. We identified whether some of these couplings might play a role when the theories flow to a fixed point. So the dynamical properties of these theories we are still studying, and how the roles of couplings or that appear in the Lagrangian play a role in that context is still an open problem that we are working on. I cannot tell you much more than that at the moment.
Okay, sorry, we don't have enough time, so maybe let's continue to ask questions in the break. Okay, let's thank speaker again.